All right, long time no see. We were talking about recursion. So remember your recursion on trees. I'm going to give you an example of a tree recursive algorithm. It's where you count the number of leaves of a tree recursively. So say we have the tree, I don't know, I actually made one. Let me give you that one. 538179. It's a BST. Doesn't have to be a BST. What I want to do is count the number of leaves. So the answer for this tree is 1, 2, 3. This is not a leaf, it's an internal node because it has a child. Even though it's missing another child. It's not a leaf. Okay, so the answer here is 3. And so if this is my example and I want to generalize it into a recursive case, I need to make recursive calls. And the only ones I can call on is this subtree and this subtree. So the recursive call for this tree is apparently, well, this one's going to give back 1, this one's going to give back 2, and the final answer for the whole tree is 3. So it looks like the recursive case is return like count leaves of like roots left plus count leaves of roots right. Which is nice. Okay, now we need to see where this breaks down so we can find a base case. So then we'll go in and be like, okay, this is going to make a recursive call to the left and the right subchild. This left recursive call, for example, will call on 3, and it needs to return the number of leaves for this subtree, which there is just 1, and so it's going to make its recursive call, because it's, we'll just pretend it can. It's got an empty tree and a tree with 1 node, a leaf, in fact. So this has a leaf, this one does not. Oh, an empty tree has no leaves. That might be useful. And then finally we get down to this case where we just have this 1 node and it's got null left and right pointers, and that one should definitely return 1 because there's 1 leaf in that tree. Okay, so it seems like for the base case we have 2. Empty tree has no leaves, and a leaf has 1 leaf, which is obvious, that makes sense. And then the recursive case is just count the leaves in your 2 subtrees, potentially empty. All right, so we can use that now to implement this function, count leaves. So base case 1, if we have an empty tree, there are no leaves in it. Base case 2, we have a leaf, in which case there is 1 leaf. Hey, we have it. Our root is it. Otherwise, we're in an internal node, and we can count the leaves of our 2 subtrees, and that will be the right answer. And so then I've built up this tree. It should print out the number of leaves for it, and we'll get back after following our fancy recursion. Three. All right. Moving on up. Now let's talk about the big 3. So, in case you were forgetting it, the big 3 is when you start managing your own memory, like when you call new inside of your own classes, you have to clean up after yourself. Okay, so you have the copy constructor, a copy assignment operator, and a destructor. And that's what makes the big 3. We also talked about the big 5. Don't forget about that. That's what the real world uses. But we'll talk about the big 3 for this class some more. Let me give you an example of a holder class that holds an array of size n now on the heap. So if I have a holder h, I don't know, of size 42, it holds 42 things. Well, my h has like a pointer to the array on the heap over here of size 42 long. Okay? So that is how we will remember our big 3. Okay, so let me go to that example. So holder.cpp. Now, here we go. I've called it holder R because it's a holder for arrays. And so here's the kind of stuff we want to be able to do with it. We want to make one, like with 42 things. We want to call the copy constructor to make h2 based on h. I'm going to call make h3 set using the copy assignment h3 to be h2, and then watch out for self-assignment h2 equals h2. We don't want that to mess anything up. So let's just remember how to implement all this stuff. What we need inside of each holder is a pointer to our array and also its size, because we want to know how far we've gone. Eventually you'll have like setters for certain indices. You'll want to know like, hey, how big is this array? That will be useful. We technically don't need size anywhere after the oh, sorry, yes we do. We definitely need size even if we're not accessing things, and I'll show you why. So here's the constructor, just makes the array on the heap of the given size, and it sets the size member variable. I guess I technically could have done this in the initializer list. Okay, copy constructor. Just remember everything. You got to deep copy stuff. We don't want this case where like h2, its array is pointing to the same one. No, we don't like that. We want it to point to a copy of that array. Okay? So we deep copy. We set our size to the other size. We make an array, a brand new array on the heap, and then we copy everything over from that other array into ours. Okay? For each index. So that's the copy constructor. We are still constructing. We don't have anything inside ourselves yet. The copy assignment operator, on the other hand, is when you are you have something in you already. Like, for example, h3 holds 43 things, but we want to replace it with the 42 things from h2. Yeah. So what we need to do is first watch out for self-assignment. If we're trying to assign ourselves to ourselves, stop. We're already ourselves. We're good. We're not having like an identity crisis. We're going to jump out of this function. Otherwise, we will remove ourselves and get ready to copy everything else in. So delete our current array and then just do the deep copy, which is essentially copying everything from the copy constructor. And then the last thing that you need to return is, because of this type, we return a reference to ourselves so that we can like chain equals sign, chain assignment operators. Okay, and then finally for destructor, the only thing that we cared about, the only thing that we made on the heap was the array, so we need to clean up after ourselves, and so we will delete ourselves. That's all. So that is a holder in a nutshell, and I haven't actually done anything with these holders. We can compile it and run it, but we're going to get no output. I guess technically if we don't get a seg fault, that's good news, but it's not a good enough test really. So that is the big three. Now you remember it again. And finally, for the older stuff, remember your complexities. So you've got this cheat sheet. Use it. Use it in detail for your data structures, for your sorting algorithms, all of this. It's super useful. It's pretty much correct except for lists. I don't believe what it says when list insertion, or really it's list deletion. The speed of that, or technically it is insertion too, because say you're trying to add something to like the middle of a list, you got to get there. You got to follow pointers, which is potentially, if it's like the middle of the list, you have to follow n over 2 pointers. That's now no longer a constant thing. So list insertion and deletion, just remember, it's not really constant. It's constant if you're like adding to the end or the beginning, but otherwise no. And deletion, if it's a singly linked list, which is the kind we talked about and implemented in this class, it's hard to delete the end because you got to find the second to last node, which requires traversal. Okay, so that's all the older stuff I want to talk about. Now let's move on to the newer stuff for this class. So all the stuff that was after the second midterm, there's honestly not too much, so let's just get right on into it. So a heap, not to be confused with the place in memory, the heap data structure is, we use it in the priority queue ADT. It's just a complete binary tree stored in a vector. So for example, here is a heap. Don't know why I put it there, but not here. Here's my example heap. This is going to be a min heap. It's going to hold the minimum thing at the root of itself. And it's a binary tree. It's complete. It's filled in. All the levels and the last level is filled in from left to right. It's actually stored in a vector. So the first thing is the 4, and you can easily get to things like the left of I equals 2I plus 1. Yeah? And the rest are similar. Like you can get to your parent, you can get to your right child as well. So it goes in order. It goes in level order. It actually stores itself in level order. 4 node is in the vector, like the heap array we called it in the lab, right? 4, then 42, then 5, then 47, etc. Okay, so that's how we store it. We think about it like this, but we store it like this, and we can move around really fast because of that. And notice that our min/max is always at the top, and the heap respects the heap property. So from every node's point of view, its left child and its right child, for a min heap, its left child and its right child is bigger. Okay? So look at every node, that's true for every node. 47, it's true. For 112, all of them. And it's not a binary search tree. It doesn't look like a binary search tree. Like 42 can be over here and 5 can be right here. It doesn't matter. As long as everything from 4's point of view, like 5 can belong there. From 5's point of view, like all of its children are bigger, so it can belong there. We're all good. We're all set. Okay. So yeah, it's really easy to get to the min-max value for a min heap/max heap. You just look at the first thing. It's heap array.at0, right? That's what we want to do. We can use that. And the operations that we have, the first one that we care about is peak. That's constant because you just return the root, okay? Same for isEmpty and getLength. You just look at the vector, see if it's empty, return its size. All constant stuff. All right. Push and pop, those are the ones that involve things. They involve percolation, but I don't like that word, so I say bubbling. Less silly that way, or maybe more silly, who knows. So let's talk about both of those in detail and talk about why they are the running time that they are. So remember, first of all, where the log comes from. The log happens because the tree is balanced. Okay? We get log all over the place because the tree is balanced. There's no other way for the tree to be stored. Like, it has to be balanced because of the way we're doing things. Like, the way we think of it. It is automatically balanced. So to get to the smallest thing, or to get to the lowest level, it's always log of n, on the order of log of n things. Okay, so let's do push. So in order to do push, we add a node to the next open location in the heap array. And so that's going to be the bottommost rightmost place. And so if we want to add something, it's got to go right here. Yeah? So let's say we're adding, I don't know, 3. And so we're gonna put the 3 node there. Let me color it something else. We're gonna put the 3 node there, and then we're going to bubble it up in the tree to where it needs to go. Okay? You bubble it up until the heap property is finally maintained again, because it's not right now. Looking from 47's point of view, it has a smaller child. That's not okay. The heap property is not yet maintained. Okay, so we're gonna bubble it up. For min heap, for max heap, it's essentially the same. You just replace smaller with greater. We're going to swap with our parent so long as our key is smaller than our parent's key. Okay, we belong higher up. So we're going to swap with the 47 because that's too big. We want the 3 to be higher in the tree. It needs to, all of the nodes need to reflect the heap property. Again, this node does not reflect the heap property, does not maintain it because it has a smaller child, so we got to swap. 42 is here now. 3 is here. And same with 4 and 3. 3 and 4. So now these all belong, from every node's point of view now, it has bigger children. And so the 3 is in the right spot. It's the new min, and we can immediately get it now if we were going to check for it. Okay? If we call the peak operation. And so the reason that this is O of H, O of log of n, is because the tree is balanced and you need to go up the height of the tree. Okay? In the worst case. okay? Because you just added the new min, perhaps. You need to go all the way up to the top, okay? And then I have to bubble all the way up to the tippy top. Okay, that's what we got there. And then pop is slightly more difficult because when we bubble down, we have options. We can go left or we can go right. Let me attempt to copy this tree. There we go. All right, I want that there, and then I want this there. Okay, so to pop, we're going to swap our roots key, because we always pop the root. We're going to swap our roots key with the bottommost rightmost node. So it's going here. We're going to swap with this node. And just like for binary search tree deletion, it's very easy to delete a node that is lower down in the tree, to delete a leaf. This is going to be guaranteed to be a leaf. Okay, so we're going to delete it, so we're going to swap. 112 goes here, and you don't need to put the 4 here, but you can, and because you're immediately going to get rid of this node. Now you can get rid of the node. So there's only indices 0 through 6 in the tree. So that node's gone. You can pop back the vector. That's essentially what you're doing to get rid of that node. And now we're going to bubble this 112 down in the tree, because the heap does not reflect, the heap property is not yet maintained. Because we have a node and it's got both of its children being smaller than it. That's no fun. So in order to bubble down, you need to keep on looking at both children and swap with the smaller one. So we see we have 42 and 5. In order to maintain the heap property, we better swap with the 5, otherwise it doesn't work. Okay, and now we look at this node. Is it yet in the right spot? It's not quite yet in the right spot, because it has 100, which is smaller than it. 256 is fine, but 100 is complaining, like, no, I belong up here. Okay? And so you're just going to keep bubbling down until you hit a leaf, or you're bigger, or you're smaller than your children. Okay? So you have all those cases. From your point of view, like, you're looking at n, you need to see if you need to bubble it. You're looking at your children. You might have 2 children, which themselves might have children. You came from somewhere. That's one case. You also have the case where there is 1 child, but not a second child. They're filled in from left to right. This one might not exist, but this one does. You have to check only it and not try to, like, don't segfault, don't go past the end of the vector. That might be another case. And then there's also the case where you're already at a leaf, you don't need to go any farther. Okay, so just remember that. That is pop in detail. And again, you might have to move down the height of the tree. Okay, log of n, because you might have to go down the height of the tree. And this is going to ruin, because I'm about to type, it's going to ruin those things. I'll put them back. Because you might bubble down to a leaf, which is the height of the tree, which is log of n because it's balanced. Yeah, it all comes together. There we go. That's a better squiggle. All right. So that is heaps. Now let's talk about sorting. All right, so again, go to the book, read about these things. What I'm going to test you on is essentially this slide. So you can come back to this slide if you want on the final. So just remember all these basic ideas for these sorting algorithms that we talked about. So bubble sort is the very simplest one. It is n squared on average because it's got 2 nested loops, and it's trying to swap things. Okay, keep swapping elements that are next to each other if they're out of order. So if I run bubble sort, it's going to keep on only looking. It's a very myopic sorting algorithm. It's only looking at the things that are right next to it. It's going to swap things. And I guess each iteration, it always puts the max of the subarray in the right spot. Like, it's going to put it there. It's going to find the max and move it to there. So that it's doing some work, but it's going to take forever to do everything. Okay, so we'll just skip to the end of that. And it's actually, it has a best case of linear time. If you're fancy. If you program it the right way, you can get a best case of O of n if the array is already sorted. Because you can see, like, okay, I never needed to swap, so I must be done. That's the idea. I don't think your book's algorithm has that special case, but there is a way. And even this online algorithm doesn't have the special case. It's just going to try everything. So there's a fancier way to implement it, but if you're trying to be fancy, you shouldn't be using bubble sort in the first place. It's a silly algorithm. Okay, selection sort is always n squared, but it's got a much better constant factor on that n squared. What it does is it keeps selecting the minimum. Select the min value in the remainder of the array and swap it into the proper spot. So let me show you that example. It's going to find the minimum. It's like, okay, it's that one. I'm going to put it there. That's where it belongs. I'm going to find it. It's going to go there. My next spot that I need to fill in is there. I'm looking at the minimum. I'm putting it there. Okay, so you can see from left to right this thing get filled in. Now it's going to be a lot faster than bubble sort, that is for sure. Okay, and you only ever need to look in this part of the unsorted array to find the next minimum. Okay, so it's always going to be n squared. So this is this table is not lying to you. It's always correct. So selection sort's n squared all the time. That's quite nice. So keep calculating the min value. Insertion sort is the fanciest, I would say, of the n squared sorting algorithms because of its best case. So on average, usually it's n squared. It's got a very good constant factor. And in the best case, if it's almost sorted, it doesn't have to be exactly sorted, like bubble sort. If it's almost sorted, I guess technically bubble sort can also be almost sorted. But if the array is very close to being sorted, like only a few things are out of order, it'll be O of n in the best case. Okay, and what it does is slightly different from selection sort. What insertion sort does is it keeps the first n or first I original elements of the array together, and it sorts that subarray between index 0 and index I minus 1, let's say. So it keeps those first few indices sorted, and that's slightly different from selection sort. See, it's whatever was in the original first few bits of the array, it's going to make a sorted subarray for just those I indices, okay? So after like the first I iterations, the first I indices are completely sorted, and then the rest of the array is unsorted. Okay, so even though there's a small thing, we're not going to worry about it just yet. We're going to move it down once we get to it. Okay, it's just like find that thing and put it in the sorted subarray where it needs to go, so by swapping. Okay? And so it's very fast. You can see it's almost done, and that wasn't the case for selection sort and bubble sort. If I run it on an almost sorted array or a sorted array, it immediately ends, because it's like, okay, I need to move this next thing to where it needs to go in the sorted subarray, but the thing right before is already smaller, so it's actually in the right spot already. So I do read the book about this. I can't really say too much for too long about all of this, but yeah, read the book, come to office hours. If you have questions, this is the stuff I want you to remember about sorting. Okay, merge sort is the nice one. It is going to, it's n log of n because it's going to split the array in half and then worry about sorting the subarrays recursively, and then it'll merge them back together into a brand new sorted array. Okay, there's a lot of different cases, like it goes and splits that subarray as well. Those get split. Those get split. It's a long process, but it's n log n always because of that splitting in half. Okay, and we talked about that a little bit. So if I show you that, it's going to split recursively halves of things, and so it's like using extra space. So it's now successfully sorted the first half of the array. Now it's working on the second half. Now it's about to be sorted. Now it's about to merge the whole thing into the final array. Okay, so do read your book about that. It's fun. That's merge sort. Quick sort is the last one. It's usually the one that most people use because it's in place. Merge sort requires extra space. Quick sort does not. It has n log of n on average. It's usually faster than merge sort, but it has a worse case of n squared if the partitioning sucked. So what quicksort does is it takes a pivot. Like it picks an element and it's going to shift over the array. It's going to make everything on the left side, like it's going to make a left half and a right half for everything smaller than the pivot and everything bigger than the pivot. So it's going to keep on swapping things until it's in that state. And then it's going to recursively quicksort those smaller arrays, because it knows, like, once maybe the pivot was 49, it held everything that was smaller than 49 in this side of the array, everything that was bigger than 49 in this side of the array. And at that point, it can quick sort this bit of the array and the right bit of the array. And once those are sorted, the entire array is sorted. Okay, so do watch the animations in your book. Do just have an idea of all this stuff in your mind. That is sorting in a nutshell. Okay, moving on to Linux and Unix commands. So the first thing, the thing that you use a whole lot in these commands are paths, like places in your file system. And so let's just briefly talk about that. You have one root directory in your computer. It's called /. And inside of that, it has some other directories like, I don't know, dev, bin, and home. And your computer has a account in home. You have your home folder. That's, for you, it's called CSCI. For me, it's called Lot Nichols. It doesn't really matter. It's your home folder. And that's a special place. It's represented by the tilde. Okay. So for example, if I go to this, make a new thing, dun dun dun. Let's get rid of that. Let's do it all over again. What I can do is I can say, I can go to /cd/. That is my root directory. I can't go up anymore with cd dot. There's nothing else there. That's the root directory. There's stuff there, and I can go inside of it. I can go inside of home, what's there, cd inside of that, and that turned to tilde, because tilde is a shorthand for your home folder. So you want to get there immediately, you're there. Okay? So that is tilde. That is your home folder. And if you want to, like, make a new file on your desktop called asdf.cpp or something, you can get there very quickly by saying tilde/desktop/asdf.cpp. Okay? So that's the idea for paths. And now cd we've talked about just moves around. cp copies things. So let's say, I don't know, let's copy, I don't know, let's make a new file. Vim foo.txt. Hi, Mom. And then we'll say copy foo.txt to foocopy.txt. That's quite nice. You can give a new path as well. You can say, I don't know, copy it to my desktop /foo. Like, if you just said the desktop, it would copy it there called foo. You can also give it a new name as well, foo on desktop.txt. And so now if I look at my desktop, there it is. Silly, huh? Let me get rid of that so as to not make my desktop any sillier than it is already. So we can copy things, we can get rid of things with remove, and then we can make new directories with makedir. Okay? And say makedir new directory. And so now there it is. We can move things inside of it as well. You just say move path to a file, foo.txt, into the new directory. And you give a directory. You can give a slash or without a slash. Move foocopy.txt to new directory. Okay, so now if we look at new directory, all the stuff is there. Okay, that's what's inside of it. All right, so do learn Vim for the street cred. But I'm not going to test you on that, of course. You may be forced to, in future classes, use the terminal for your coding entirely. So get comfortable with a terminal editor that doesn't suck, like Nano does. Okay? Nano is no fun. Use Vim. Let's see. Vim or Emacs? Vim is the hotter thing at the moment. But Emacs is... the theory community loves Emacs. Okay. Make is something that you should definitely be familiar with by now. I've been using it. Maybe you haven't been looking at my make files that I've made for you. You definitely should. Okay? You need to go back and learn make. Wink, wink. You might see something about make files on the exam. So make is all about making it easier for you to compile things. And perform what's known as separate compilation. So if you have, for example, a.cpp and b.cpp, and you want to compile those, you can go through intermediate forms. You can make a.o and b.o, which are compiled forms of just a.cpp, compiled forms of just b.cpp. And then you can link them together, okay? You link them into a final executable, maybe called main or something. And so let me just show you that. Here's my a.cpp. It holds the main function. It calls foo, which is declared in b.h and is defined in b.cpp, just returns 1. So if I want to compile these things, I can say, I can make a makefile, okay? I can make a makefile, and I can say, okay, it always goes, remember the rules. It's always target, the name of your target, the thing you're trying to make, your requirements in order to make that target, and then you tab over, this is a tab, not spaces, then you give your commands to like make the thing that you wanted, potentially multiple things. You might need multiple commands. So yeah, and separate compilation is super nice because you don't have to recompile a.o when you only changed b.cpp. Okay, you just have to relink against the recompiled form of a.o. Okay, that is the idea. And so if what you want to make is main, you say, all right, I require a.o and b.o to make main, and then you'll give the command to make main using those requirements. And then for a.o, if you don't have that yet, you need a.cpp to make it. And that's how you call the compilation stage of G++ to make the .o file. Same for b.o. And now if I say make main, it's going to compile everything. It notices that it doesn't have a.o yet, and so it goes and runs that rule. It's super nice. That's how it does it. That's how it knows. And if I change something, like say, I don't know, cout hi mom, it'll only recompile the stuff that's changed. It's like, okay, only A needs to be recompiled into a.o. b.o doesn't need to change. I'll just recompile a.o and then relink. That's what make gives you. Okay, so understand how it works and how you might use it to compile things. Okay, I might ask you to make a rule. Okay, so that is Linux and Unix commands in a nutshell. Let's move on now to inheritance. And we're almost done. So inheritance is when you have a parent class and a child class. You have a hierarchy of things, and you want to reuse code across these parents and children. Okay? And the other nice thing about inheritance that you have access to is virtual methods, and those let you override behaviors. So for example, my best example is Apple just came out with their new Apple Silicon processors, and all the cool kids want one. I will wait. Let us make an inheritance hierarchy for classes about Apple products. So the parent class will be Mac Laptop. Okay? So ML for Mac Laptop, and it has some fields that all Mac laptops should have. Like every Mac laptop should have a price, it should have a battery life. And it'll have some methods as well. Get the price, get the battery life. Hey, does it run Windows? Because some of them do. The Intel ones do, the others don't. Sorry, it's the wrong arrow. And then we can make MacBook Air that has an Intel processor that can inherit from Mac Laptop. This is MAI, I guess. And it has a new field, but it inherits all of these, which is super nice. It has like processor model. What kind of Intel processor is it? Store that. And then also, we'll have MacBook Pro M1 with a new processor, and it doesn't have any new fields, but it'll have some new methods. Like we're going to override runs Windows because it can't run Windows. And then we'll also make a new method called is owned by a hipster, because anybody who's bought one so far is most certainly one. Okay, so that'll just return true. And so, yeah, it just inherits all this stuff, and that's my best example of a class hierarchy for you. All right, so here's my inheritance.cpp, and let's take a look at it. So, a Mac laptop. Remember, we're going to make things that can be inheritable, fields that can be inheritable, that we can see in our subclasses. So we no longer say public, we no longer say private, we say protected. Okay, so we have prices and battery life, so those are protected things. And so the constructor for a Mac laptop takes the price and the battery life and sets them. And we have getters for those. They are const. And then let's make a function that can be overridden. A virtual function is one that can be overridden. And let's make it be called runs windows, and our subclasses can override that. And now we'll make it a pure virtual method by saying equals 0. We won't give it an implementation, which means if you have a pure virtual method, Mac laptop is an abstract class. We say it can't be instantiated. You cannot make an object of type Mac laptop. If I try, I will get errors. You see it? Variable is an abstract class. It won't compile. This is fun. It's a very long error. It's like, first of all, I didn't use the right constructor, so like 42, 42. Second of all, it's abstract. Mac laptop is abstract because of this virtual method it's telling you. Okay? Because the following virtual functions are pure. Okay, so we can't do this. All right. So then let's make our subclasses. MacBook Air Intel inherits from Mac laptop. It has one extra field, a processor model. It has a constructor that calls the constructor for Mac laptops to build up the price and the battery life to store those. You can do that. You can call your superclasses constructor. And then we'll worry about our new field, which is the processor model. We'll set that, make a getter for it, and then return true because an Intel processor can run Windows. So we'll say we'll override this run Windows method, this virtual method that was defined up here, and we'll have it return true. Okay? And then same for M1, MacBook Pro M1. It's a Mac laptop. It has no new fields, so we'll just call the constructor for Mac laptop to set the price and battery life. And it does not run Windows because it's not an Intel processor. And it is most certainly owned by Hipster. Okay, so now we can make these things. Make a MacBook Air Intel, potentially has 8 hours of battery life. It has an i5 processor, let's say. And then the new MacBook Pro, it's probably very expensive, and it probably has a much longer battery life. So then we can start printing out things like get the processor model for the MacBook Air Intel. It's i5. We can get the price. And these are all not implemented in this class. They're implemented up here. Bam. We're calling methods that were inherited. We can call the run Windows method that we overrode. Like, yes, it does, 1 for true. And then same for this guy. Get the battery life. Does it run Windows? No, it does not. And then call one of the methods that we made. Yes, it is owned by Hipster. Things like that. So that is my example of inheritance in a nutshell. And you can put all these together in like a vector of like either references or pointers. And just call the Mac laptop stuff. Okay, you can be like v.at0 dot runs Windows or arrow runs Windows. One of the nice things about inheritance is that polymorphism, if you remember that word. We can treat subclasses like the base class. Like both of these are, by virtue of inheritance, they are Mac laptops. So why not say that, and why not use them? Oops, cout, not const, excuse me. And so we can just, like, we know that Mac laptops have a runs Windows method, because they will be part of some subclass that has implemented and overrode this method. That's the idea. Okay, so we can think about these from Mac laptops' point of view, and then we can store different subclasses. It's super nice. Inheritance is cool. Okay, so that's my example of inheritance. And now for the last example, Huffman coding. Okay, so let's talk about that. So technically, we say Huffman tree, but it's really a trie, pronounced try for no good reason. And let's talk about it. So here is an example trie based on a Huffman tree. It's given an encoding for a bunch of different characters. And so if we were trying to make D, for example, if we wanted to like encode the word, I don't know, rad, using this tree, we would find the R, and the way to get to the R is we say 1, 1, 0. So that's the binary form of R. 1, 1, 0. So we're going to write that to our file in binary. Write those 3 bits, and then A is a 0. It must have appeared quite a lot. So we have a 0, and then D is 1, 0, 0. Okay, so now in less bits than it would take to say rad as a C++ string, because that would take 3 characters, and each character in C++ is 8 bytes. This is 7 bytes. All right, sorry. Each character is 1 byte, 8 bits. This is 7 bits, and we're storing the same thing. So compression is lovely when it works. Okay, so one way to compress things is to make these tries based on an input string. So to generate a Huffman code, we have to make the Huffman tree, and then fill it in. So first thing that we do is we calculate the frequency of every character in our file. So let me have an example file, and it will hold hi mom without spaces. It's easier that way. And then we're going to go and we're going to count the occurrence of each of these words. So we're going to make a frequency table for each character. It'll be like, okay, H's, those were, there's one of those, there's one I, there's 2 M's, there's 1 O. Okay, so 5 characters total with this frequency table. And then what you do for Huffman coding, it's a really nice example of all the data structures that we learned, or just like how to combine them. What we do is we make tree nodes for every character and its frequency. Okay, so we make some nodes, and we're going to plop them in to a priority queue. So right now, initially, the priority queue looks like this. It's holding just separately leaves, like H holds 1, I is frequency 1, and then M is frequency 2, then that's a 1 and a 1. That should have been an O, sorry. Then O is frequency 1. And then what it does is, after you put them in a priority queue, you plop them out, you pop them out based on their frequency, and you combine them, the lower frequency ones, it's a min priority queue based on frequency, and you pop those two nodes with a min frequency, and you combine them into a bigger Huffman tree node, because they weren't as frequent and they can be farther down into the Huffman tree. Okay, so we'll go from this to, like this was the priority queue. If only I could write things. That's our PQ. It goes to, let's combine H and I. Okay, those are both minimum frequencies. So I'll take H and I'll take I and combine them into one super node that contains H and I as leaves, but it's holding the frequency of both of them. So H and I together, their frequency is 2. So it's like another big character or something. Then we've got O with 1 and M with 2. So then we'll take the O and one of these. So maybe we'll take the O and the M, we'll combine them. Okay, so that'll be the next priority queue. That's another version of the priority queue. Here's another version of the priority queue. And let's say we'll combine 1, which is definitely the min frequency, and maybe m. So we'll take O1, M2, and we'll put them like this into a frequency 3 node. And that's our priority queue with also the 2 H1. I1, sorry. Tree. So we got 2 trees, and we're going to combine them. We're going to plop them both out in our final iteration and make the priority queue look like this. It's going to hold. Well, we pop them in one first, so maybe that'll be the left side. H. Got the 2, H1, I1. Then we got the 3, the O1, M2, and then we finally have 5. And so this is how we will encode all our stuff. We could have been fancier. Based on how we pick these, maybe we could pick the, we could have combined these and then the M would be by itself or something. But it's still nice, it's still correct. So yeah, once you're done, you have a priority queue with just 1 element in it. It's a big tree with 1 frequency value. That is the length of the file, so it's 5. Hi mom is 5. So now we can read things off of this one thing. Zeros are to the left, 1s are to the right. So I want to encode hi mom, which would normally take 8 times 5 bytes for chars. Instead, it'll be H is 0, 0. I is 0, 1. M is 1, 1. O is 1, 0. M again is 1, 1. So how many? 1, 2, 3, 4, 5, 6, 7, 8. 1 byte and then 2 bits. That's 10 bits. Instead of 8 times 5, which is, what, 30, right? 40, sorry, which is 40, which would be the uncompressed version. Okay, so that is very nice. It is compressed, and that is Huffman coding. It's an example of using a bunch of custom classes, tree nodes, as well as priority queues ordered in a certain way, a min priority queue, a min heap based on frequency. And then the tree that we build is really a trie, and left and right, they give the encoding. Okay, so we can now make the encoding table if we really wanted to, even though I made this already. So now it's frequency. The encoding is H, I, M, and O are 0, 0, 0, 1, 1, 1, and 1, 0. Okay, so that's Huffman coding in a nutshell, and that brings us to the end of the review. So you have made it. You've made it to the end of the class, of all the topics. Hopefully everything is making sense. Please come to office hours if anything is still fuzzy in your mind, and I will give you further examples. Okay, that's what I want you to do, and with that, we have reached the end. So these are the final memes I have for you. Good luck on the final if I don't see you until then. Do come to office hours, ask me things if you'd like, and yeah, enjoy. I will see you later.